Jai Hind all, myself Amita Asthana, Assistant Professor in Ajay Kumar Garg Engineering College. In this video lecture, we will discuss two important topics from the subject Digital System Design, which are very important and very useful for solving the K-map. One is the tabulation method, and which is also known as Quinn-McCleskey method. This one. This is 4 variable. I will take the solving of 4 variable K-map, and it's an entirely different method as usual we solve our K-map problems. So it's a kind of different method to obtain the simplification for any given minimized or maximized terms. And another topic which is entirely different from solving of K-map, that is Hamming code. So first of all, I will discuss about the Hamming code, and then I will take the Hamming code generation, and if the Hamming code has been propagated through the environment and some error has been occurred, then how to detect that particular error in the data bit which has been sent via the environment on electromagnetic waves. So here let us move ahead for both the methods, and both the methods are entirely different with each other, but they are very interesting to be understood. So here we go. Now coming to the introduction part of the tabulation method. So K-map becomes sometimes more complex if we solve for 5 variable or 6 variable and or more. So so 5 or 6 variable problems we can go for the tabulation method. This particular method is also known as McCleskey method, and here the minimized expression can be obtained by preparing a series of tables. So here in this particular method, it is a tabular method, because we are preparing a series of tables in it. So how we go and what should be the problem and the concept, let us understand. So let us consider the function which is summation of m. We are given the minimized sum of product, that is 0, 1, 2, 3, 5, 7, 8, 10, 12, 13 and 15, let's say. And if I want to go for the 4 variable K-map, it is also easy to solve, but still we are doing it using the tabulation method or Quinn-McCleskey method. So here first step 1 should be, first of all, what are the min terms which are being given. Let us say we are given with 0. So I will write the binary of 0. Similarly, the next is given as 1. So I will put the binary of 1. And similarly, I will write all the binary terms of all the given, the min terms. So for 15, this has been written like this. So first of all, my first step would be that I will write the binary of all the min terms. Okay. Now next, step 2. Coming to the step 2, after writing all the terms in the binary form, I will see this particular has no 0. This is having 1. This is having 1, 1. Okay. And this is having 2 ones. This is also having 2 ones. This is having 3 ones. This is again having 1, 1, 2 ones, 2 ones, 3 ones and 4 ones. So these terms are the index. Number of ones are the index of the terms. So I had min terms. Okay, I had min terms. I wrote the binary form for every min term. Then I calculated the index of all the binary min terms. Now, next step is I will arrange the terms in increasing order of their index. So next step will be I will arrange them in the order of their index. So here I will make the first list. So this is how I will continue. Let's say I was having 1, 0. First there was 0 ones. Okay. So I have made one group. In all these 1, 2 and 8, see here 1, 2 and 8. These three terms are having 1 ones. So it is my another group. So I will put in another group, that is 1 ones. Okay. Then 2 ones, group of 2 ones. Then group of 3 ones. And then group of 4 ones, like this. So here I have made the groups, and this I will call it as my first list. This is my first list, right? So I will write the min terms here. I will write the groups according to their index. I will make the group according to the index. Okay, one index min terms will be written in one group, two min term, 2 ones min term can be put into the another group, and like that I have made my 5 groups. I have made 0, 1, 1, 2 ones, 3 ones and 4 ones. So that was my first list. Okay. Now here this first list corresponding to the individual value. That means if I have a 4 variable K map, then I will write it as like suppose one min term I can write it as 1 B C bar D. Any example I am taking. So this particular is my one single term. Okay. Now next step would be I will be making the I will be making the second list, right? So here I will see one second. So here I will see comparing this group to this element, this to this one, this to this one. I will compare my each element of any group to every element of the another group. How? So the procedure is, let's say I compare 0 and 1. Okay. If I compare 0 and 1, I can clearly see these are same, but here it is a change. Here it is a change. So I will focus on only one change. Only one change I will focus, not more than one. Exactly one change I will focus on. So what I did is, like 0, 0, 0, 0, there was a 1 bit change at the D position bit. So I will make a pair. I will make a pair like this. While I am making the pair, I will write 0, 0, 0 and dash. Dash is the position of change, right? So I will take the 0 and the 1. Since I have made the pair for 0 and 1, I will take both the values that I have made the pair, and I will write my pair like 0 and 1. I have made a pair 0, 0, 0 dash. Similarly, I will compare 0 to 2 and I will write 0, 0 dash 0 and I will make a pair, and I will again take my 2. again comparing 0 to 8, I can see very clearly here is the bit change and rest are same. So I will just write dash 0 0 0 and tick. So similarly I will compare my 1 2 3. So if I compare my 1 2 3, here it is the change. So I will write 0 0 dash 1 and I will tick my 3 also. Similarly I will compare my 1 to 5. Okay, 1 to 5 and I can see 0 dash 0 1, 0 dash 0 1 and I will tick my 5 also. Similarly 1 to 10, 1 to 10 if I see, then I can see there are the 2 bits change, that at the first and then the third. Okay, so sorry, 2 and 10 only 1 bit changes there here, so I will tick my 10 also and I will make a pair. Similarly 2 and 12 I will see, and 2 and 12 are 2 bits change, so I will not go for 2 and 12 group. See, 0 and 1 is a bit change, 0 and 1 is a bit change, so I will not go for the pair of 2 and 12. Now coming to the, so this group comparison with this group has not been done yet, because one I have compared to all the elements, but now it is now turn of 2 to be compared with all these, right? And then 8 to be compared with all these, and I can see 8 and 10 can make a pair with this 1 0 dash 0, and 8 and 12 can make a pair with 1 dash 0 0, like this, and I will take my all the 12 and then 3 and 7, 3 and 7, then I will compare these two groups 3 and 7. I can see that there is a 1 bit change here. So 3 and 7 can make a group and I will take my 7 also. 3 and 13 can, no, you cannot make a group because here there are 2 bits of change and 2 bits of change is not allowed at all. So I cannot make this particular pair, and then I will go to 5 and 13. So 5 and 13 can be paired because there is only 1 bit change, that 5 and 13 here dash 101 dash 101. So here it is wrongly written, actually 1 dash 101. So here it should be 0, and then 15, 7 to 15, 7 to 13 to 15. So every time I compare, every time I make a tick, similarly I will go for the next third list. But second list is of pairs. That means pair which we make in the while solving the K-map, the quads which we make while solving the K-map, and octet which we solve while making the K-map. So the third list I will make, which will define the quads like this. So here it is ABCD. I will write ABCD. Now again I will see for the 1 bit change only. I will see for the 1 bit change only, right? Let us erase all these. Coming to the quads, the same process will be followed. Like I will compare 0 1, 2 1 3, 0 1 2 1 5, 0 1 2 2 3, 0 1 2 2 10, 0 1 2 8 10, 0 1 2 8 12. But if I will compare like this, it may take me so much of time and hard work. So here some simplification is also required. Like from first list I need to compare like this as we compared, but from second list to third list we can take our common sense and that we can go for it. Like here, see the common dash from first group and second group. The common dash I can compare. So I will see 0 1 2 3 whether they are with the 1 bit change or not. Yes, of course this dash is matching, this 0 is matching, but here this is matching, but here this is a 1 bit change. So 0 1 and this 2 3 are making pair, and I will take 2, 3 and 0, 1. So I will make a pair 0, 1, 2, 3. Similarly, I will compare by just looking at the common dashes from any group to another group, like this. So all to be ticked. Similarly here 0, 2, 1, 3, 0, 2, 1, 3, 0, 0 dash 0, 1 dash dash. So it is coming like this, tick, and then 0, 0, 2, 2, 8, 10 dash, common dash. I will compare only common dashes here. So obviously dash 0 is the thing. So I can write here as dash 0, 0, 8, 2, 10 can be compared, and similarly I can go for all the sets. Maybe while comparing this, see, this 8, 12 is not making a quad with any another element of any other group. So it will be left. Here it is also being left. Now here from third list to fourth list, see, two dashes are common, but they are like same. So there is no point of going ahead of for the fourth list, or I can say for the octet. So I can stop at the quad point, and now I will focus on what are those pairs or quads or single element which have not been ticked by any pair, or which were not able to make any kind of pair with any another element of any other group. So here what I can write it as that I will write like this is left. So this is nothing but A, C bar, D bar. Okay. This was left. So I will write A, B, C bar. That's it. Here I will write A bar, B bar, A bar, B bar, same. So this B bar, D bar, B bar, D bar, A bar, D, and B, D, B, D, right? So I have now 1, 2, 3, 4 and 5 and 6. 6 prime implicants. 6 prime implicants, right? If I have 6 prime implicants, now I will make my pie chart, and from these prime implicants I will fetch my essential prime implicants, that is EPIs. So from these PI I will fetch my EPIs. So now coming to the next procedure, so that would be I will write A bar, B bar, B bar, D bar, D, all 6 I will write, and all the min terms from here 0, 1, 2, 3, 5, 7, 8, 10, 12, 13, 15 I will write here 0, 1, 2, 3, 5, 7, 8, 10, 12, 13, 15 like this. And let's say A bar, B bar, what was that? Let us see. A bar, B bar. A bar, B bar is nothing but 0, 1, 2, 3. So I will cross 0, 1, 2, 3. B bar, D bar is 0 to 8, 10. So I will write 0 to 8, 10. Similarly, A bar D 1, 3, 5, 7. So here it is 1, 3, 5 and 7 like this. Okay. Then coming to BD 5, 7, 13, 15. 5, 7, 13 and 15 like this. Then A, C bar, D bar. A, C bar, D bar is 8, 12. So I will cut 8 and 12, and similarly A, B bar, C bar is 12, 13. I will cut like this. Now another step is little bit more important. This was the pie chart. I have completed my pie chart. Now I will see how to get the essential prime implicants from my all six prime implicants which I found from the last exercise of making the tables by just comparing one bit change or one bit change only. So now coming to this. So first of all, I will see which are those columns having only one cross. So I can find this 10 and this 15 are those columns which have only one cross. Okay. So let us take this one. I have ticked this one. So when I ticked, I went up to this B bar D bar. I wrote B bar D bar, and then while moving towards B bar D bar, while moving to B bar D bar, I saw this line is also cut by due to this two line is also cut, and this line will also cut, right, like this. Okay. Now next again I will do the same process. First only one cross I will search in which column it is appearing, and then I will write my this one. I will tick my this line, go to the BD, and I will write plus BD here, and then I will move towards BD. I saw one cross, ticked the line, and then I saw one cross, ticked the line, then I saw this particular cross and ticked the line. Okay, now one line is remaining, 3 is remaining, 12 is remaining, 3 lines are remaining. So I will search that particular line which can cut more vertical lines. Okay, see how. Let us see if I take 12th line. So 12th line is having two crosses. Either I can go for A C bar D bar, or I can go for A B C bar. So if I go for A C bar D bar, then this line can be cut, but this is also cut and this will be selected. Again, if I go for the next one, this is also already cut and this will be selected, but my choice is I will have to take it, and then I will go and write A C bar D bar. Now one more line is remaining, two more lines are remaining, 1 and 3. For 3 I have choice for A bar D and A bar B bar. For 1 I have choice for A bar D and A bar B bar, right. Let us see if I take this 3, is it able to cut this also? Yes, of course it is able to cut. And if I suppose I take this 1 and I take this A bar B bar, so it is also able to cut this one. So here what I can do is I can have option, I can go for any one. So A bar B bar I will go, let's say this one, and while taking this A bar B bar, this line is cut, this line is cut, this line can also be cut, all the lines are cut, and I can write my final expression or final solution. Okay, so that was the tabulation method. Now coming to the Hamming code, the next topic, the next complex topic I can say, that is Hamming code, which is error correction and error detection, right. So it is especially for this particular, we will talk of 1 bit error detection and correction. 1 bit error detection and correction. So if 1 bit I can identify this while transmitting a particular data, there was an error and the bit should be 1 but it has been transmitted as 0, then I can flip the bit and get the correct data. So detection is more important. So what I will do is I will be adding some parity bits to my main data so that the detection can be done, and if the detection can be done, then correction can be automatically done by the receiver. So here is the game between the transmitter and the receiver. Transmitter is sending some data, making the Hamming code of the original data, and this Hamming code can be generated by adding some parity bits to my mainstream data. So here coming to this one. So Hamming code, this is used for error detection and correction, especially for the 1-bit case we are having. We are discussing only 1-bit error correction and detection, and then using the concept of parity bit. So parity bit concept is also important. So we have two types of parity. First is even parity method and second one is odd parity method. Okay, even parity and odd parity. Let's say I want to transmit a particular bit stream. See here, this is the bit stream 11011001. So this particular bit stream I am transmitting, number of message bits are 7, number of extra parity bits. So how to calculate how many parity bits I should add? So there is a formula. I will have to verify the formula to add my parity bits. So in this case I will take the 2 raised to the power p is greater than or equal to 8 plus p. So this should be this should be done for this, and from 8 where it is coming, this is the formula. 2 raised to the power p is greater than m plus p plus 1. M is 7, this is 1, and p, now I need to find out this p. Suppose I take p is equal to 2, then 4 cannot be greater than m plus p plus 1. 3, 2 raised to the power 3, 8 cannot be greater than m plus p plus 1, but 4 can be greater than 8 plus p. So if I take 2 raised to the power 4, that is 16, that is greater than 8 plus 4. So here I will take 4 parity bits. So in this case I need to add 4 parity bits to my main stream data at the transmitter circuit. Okay, so total number of bits are m plus p 11. So instead of transmitting only 7-bit main data, I am transmitting my data with additional parity bits added to the data. That means the data earlier I was having with 7 bits. After adding parity bits, 4 more parity bits, now the data which is going to be transmitted via air, that will be 7 plus 4 is equal to 11. Okay. So instead of transmitting 7 bits, I am transmitting 11 bits from the transmitter. So how to do it? So let us see. This is 2 raised to the power 0 position, 2 raised to the power 1 position, 2 raised to the power 2 position, and 2 raised to the power 3 bits. All the 2 raised to the power positions are the parity places. P1, P2, P3 and P4. Since I am adding 4 parity bits, so these are the positions for my parity bits. So I will write first of all 11 from 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So P1, P2, P3, P4, and then my data was 11011001, 110100. So after writing my parity bits, I will fill the gaps with my original data. Now I am very clear that whatever data I am going to transmit is like this. P1, P2, 1, P3, 1, 0, 1, P4, and 0. So this is now going to be transmitted, and now at the receiver it will be received. Okay. So how to find the parity bits? So P1, P2, P3, P4 are also the bits, no doubt. So how to find my P1? Okay. So for P1 is 1, 3, 5, 7, 9, 11. 1, 3, 5, 7, 9, 11. P2 is 2, 3, 6, 7, 10, 11. 2, 3, 6, 7, 10, 11. P3 is 4, 5, 6, 7. Okay. And then P4, 8, 9, 10, 11. Okay, right. So P1, P2, P3, P4 are justified and they have been decided that these values to be taken, these whatever the bits at these values, that will define. So coming to the very important step now, that is what should be the values for P1, P2, P3 and P4 for the even parity. That means when I am sure that I am going to work with even parity, then what should be P1, what should be P2, what should be P3 and what should be P4. It's 0 or 1 I am talking about. So here, see, so that's 1 is my P1. I will write from here. 3 is 1, this is 5 is 1, 7 is 1, 9 is 0, 11 is 1. Okay, right. If I have transmitted with even parity, then P1 should be 0. Why? Because this stream is having 4 ones. If I will take P1 as 1, then it will make it odd. This stream will get 5 ones. That should not happen. I am working with even parity. If I would have worked with the odd parity, then I will be taking this P1 as 1. But here since I am working with even parity, so P1 should be equal to 0. Similarly, P2, 2, 3, 6, 7, 10, 11. So here from here I will write P2 at 2 position. P2, 3 is 1, 6, 0, 7, 1, 10, 0 and 11 is 1. Now this P2 should be 1 because here 3 ones. So I will make it even and then I will take P2 as 1. So similarly I will find for P3 and then P4, and now Hamming code can be written like this. So my code was here, this is P1, this is P2 and this is P3 and this one is P4. So this is my Hamming code generation at the transmitter. Now coming to the detection part, parity check. Again I will apply the same formula for error detection. Let's say I have transmitted the data has been reached to the receiver. Now receiver, how if some error has been occurred in the environment, then how the receiver should know that what was the error which has been occurred in the environment and how it should be corrected. So here again I will take the same sequence for P1, 1, 3, 5, 7, 9, 11, all where the ones were there in the last column, P2, P3 and P4. P4, 8, 9, 10, 11 like this. So here coming to this, at 1 position it was 0, 2, 3 position it is 1, 1, 0, 0 and 1. 3 ones. So 3 ones, that means odd, but I worked with even. So here the error is there. So this is wrong. Okay. Again I will check for this. This will also get wrong. This will also get wrong, and this will be correct. Where it is wrong, I will write as 1. And I will take the ascending order, rewrite the sentence and check the 7th bit, and I got that error was in 7th position and the data was being 7, it was 1, the received was 0. Now I can correct my data at 7th position, and hence we can correct the data using Hamming code. Wherever it is wrong from even, it was even, it has been defined as even, but it is making it odd, then it should be wrong. And it was defined as even, it has been taken as even. then it is correct, and then flip the take from bottom to up and then write the sequence and get the error bit position. So it is how we can correct the error using Hamming code. Thank you.